Okay, this is problem 1-34. Let me just make sure the mute's off. I want to go over this one here. I want to talk a little bit about drawing these free body diagrams here. If you get something like this and you're looking to find out what the load is anywhere along here, you can draw your free body diagram as 4 kilonewtons anywhere along here. That's what the load's going to be until you reach this point here. You can also come back this way. And I'm going to show you it doesn't make any difference. If I start right here, and I'll just draw this as a small little rectangle, and I go here all the way over to here, then if I apply my load of 4 kilonewtons coming in like here, then I would have to balance it out going this way too. Now let's come in from the other side and I'll prove it exactly 4 kilonewtons. Let me make that vector look a little bit better too. And I'll label these. So again, it'll be 4 kilonewtons. And remember, everything has to be in equilibrium no matter what. Now if you come in the other way and draw a rectangle, basically you have this, and then all of a sudden you have another rectangle kind of like this. Something kind of like that. Now look what happens here. You have 8 kilonewtons here. When you get to this point here, you have 12 coming back in, because you got 6 and 6. So I have 6 here, I got 6 here, I have 8 here. So I get 8 going this way, 12 going this way. 12 minus 8 gives me 4. So in this case, I would have to have 4 going back to balance it out. So again, if I'm going to cut it right here, I could do it coming from the left or coming from the right. It works the same. Alright, on this one I went ahead and solved the problem. Again, made note to draw the good free body diagram. So if I'm going to solve for D, I'm going to draw it. I got 4 kilonewtons coming in. Oh, I don't show that. I got 4 kilonewtons coming back. So at this point, anywhere along this beam here, between here and here, I'm going to have a load of 4 kilonewtons. It's going to be compression. Here I'm going to have 8 kilonewtons going to the right, so it has to be in tension because the arrows are going away. So all that you have to do on this one is P over A, and that's all I did here. I could find out what my average stress is. And remember, when you do P over A, you're getting average stress across that cross section. That gives you 13.3 megapascals at C. Sorry, it's C. So I'm sorry, not C. At D in compression, and 70.7 megapascals tension at this point here. Alright, problem 1-42. A problem like that, you need to find out what the load is going to be anywhere along here, because the question might ask you what the shear stress could be here. It could even ask you what the tensions are going to be here. Okay, so what I'd recommend, draw yourself a free body diagram, which I did here. I let this be my point A here, B here, and C here. Treat this as all one system. I got 40 kilonewtons going to the right. I apply that. I draw the way the vector I think it's going to go. If I get it wrong, it doesn't matter. At this point, sum your moments around this point and set the moment around there equal to 0. When I do that, all I have to do is solve for FBY, which I do here. And I let anything goes this way be negative. So I got negative 40 times this distance, its moment arm 1.5, plus FBY times this distance 2. Solve for FBY, I get 30 going up. At that point, I sum the forces in Y, and I find out that FAY has to be going down 30 kilonewtons. Sum the forces in the X direction. Here you have rollers, so it cannot take any load. So FAX has to go back the other way to balance out the 40 kilonewtons. So when you get a problem like that, your loading here is the combination of these two. So when I have a 30 kilonewton and a 40 kilonewton being applied here, and I'll just label this will be my 30 coming down. Here I have 40. What you want to do is to use Pythagorean theorem and find out what the sum of those two would be. Let me make that a better. This would be 40. Sorry, it didn't look like it. So what you would do in this case, you got 40 going this way, you have 30 going back this way. Use Pythagorean theorem right here, and you would figure out very quickly that this is in 50 kilonewtons. Now, to find out what that is, I said since the pin A is in double shear, if it's in double shear, you can either double the area or you can reduce the load by 1/2. I would probably recommend you double the area. So I have the load, 50 times 10 to the third. I double the area, so I use pi r squared by double it. That gives me 50.9 megapascals. Okay, also while I was here, I showed you here that you can find out what the load is in each one of these members. I said member A, B would be tension 40 kilonewtons, and the reason being is because if I'm applying 40 here, this has to carry the vertical load because this cannot carry any horizontal load. So this would have to be 30, this would have to be 40 because this can only carry the load. Now if I want to find out what the stress or the load is here, just sum the forces at B or C, either one. They're going to get the same thing. And when I do that, I got 30 kilonewtons coming down. So the only way that to eliminate the 30 newtons to get everything in equilibrium is this force here, which is that force in that beam times the sine of that angle, must equal 30. I did that, and I found that the FBC was about 50 maybe kilonewtons in compression. Alright, let's look at another problem here. This problem, I think, let me think about that. I can't remember if this problem was one of your assigned problems or not. No, you had 42. I did 43 here. I'm going to talk a little bit about this if you get a problem like this on a test. Treat this thing as one big system. So I drew a free body diagram of the system itself. I took mass times gravity here coming down. I have the cable coming this way. All you have to do now is take the moment around here. That's going to give me 1470 times this horizontal distance, which I did was 1.2. I got that from here. That's going back this way here, so I let it be negative. This can only, the moment is the horizontal component of this. The vertical causes no moment because it goes right through A. So if this is 30, I made this angle 60. So I said T times the cosine of 60 right here times this vertical distance, which is 1.2 plus 0.6 is 1.8. I solved and I got the tension 1960. At that point, just sum your forces in the X. So if I sum my forces in the X, I'd have 1960, and I label that times the cosine of 60 going left. So FAX has to be 1980 or 980 going to the right. At that point, sum the forces in the Y direction. You'd have 1470 coming down. You'd have 960 times the sine of 60 coming down right here. I solve for FIY, and I get 3167 pointing up. The first question was CF. It says determine the average normal stress in CF. Well, all I have to do is take the loading here and divide it by the cross-sectional area, which I did here. That gave me that stress here. Now, same way when you're doing your shear stress at A or any joint, you got to make sure you get all the loading. So I have this one and this one. So what I did was I used Pythagorean theorem. I found out what the resultant would be of the two. I got 3315. Again, it's in double shear as noted in one problem. I think it's 141-44. So I take the load divided by double the area. That gives me 58.7 pascals. Okay, now while it's here, I'm trying to think if it even asked me for this. Yeah, it asked me for the strut at BD. If it asks you for like a strut in BD, just isolate this beam by itself. Take a moment around C and just see what loading is required to push vertically to get this. I think I do that down here. Draw the beam. I got 1470. I got 1.2 coming across. I got the force FBD is pushing up here. The angle is 45 degrees. And it's 45 degrees because it's going over 0.6 and down 0.6. Take your moment around here. Only thing I'm interested in is the vertical component of this, not the horizontal, because the horizontal has no moment arm. I get my minus 1470 times 1.2 plus FBD times the sine of 45, which gives me the vertical load times 0.6. I solve for FBD. I get 4157. Again, simple problem. 4157 divided by cross-sectional area gives me the average normal stress in that beam, in that member.